All right. All right, so are we good to go another time? All right, good. All right, so I think we got the camera going. All right, so where was I? Oh, so it's the change in flux. So I'll say it one more time, that as the ring is going down, it opposes the change. The flux is coming out because North Pole is pointing up, so we want to get some flux going down. That means we have to have current in a clockwise direction, as we would be standing on top of it watching the ring drop. And so that's the Lenz's law. Here's an interesting question. How can a long piece of wire be wound on a spool so that the wire has negligible self-inductance? Right, and I heard somebody say here you would have to have an equal balance of clockwise and counterclockwise. Exactly. Because one direction being the same the whole time just increases the flux. And so if this is the spool that we're going to wind the wire on, maybe we would do something like this. We would take the first winding and go around, and then after we have one winding, we'll just kind of switch directions and go. Let's see, so if I go over the top, and then does that make any sense? So the first one, it goes over the top. And so if the current is this way, the current would go up here, down here. Then this one would go around the other direction. And so this one here is over the top and behind. Then this one is in front and then behind. Does that make any sense? Counterclockwise, right? Or maybe kind of less than perfect, because they would be spread out over more space, is maybe we'll do a bunch of them clockwise, and then about halfway through we'll loop around and then do counterclockwise. So it'd be up, 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 down, down, down. How about that? Maybe that's easier to see. But the problem is that's probably not as efficient, because they're not all right next to each other, and so the flux from this one probably doesn't go through that one. But I noticed this is how Don put the answer, so I would certainly be willing to accept either one of those. You got the idea that we just have to match that flux. And by the way, in a practical sense, anybody ever take apart, say, a speaker system or a DSL line or one of your lightning connections on your iPhone? And what you'll notice is that as the wires come, they're not just two straight wires, they're twisted. They're a twisted pair of wires. Why? Right here, so the flux cancels. Because what did we learn about an inductor in a circuit? Doesn't it oppose the current? And so what if you have this lightning connection and you want to send data from your phone to your computer fast? What does the inductance do in those wires? Yeah, it slows down the speed at which you can do it. And so the smart electrical engineer will take the wires and twist them, and therefore reduce the amount of self-inductance, and therefore increase the transmission speed of your data line. And so a twisted pair is much, much better than a non-twisted pair. And then that's what this is kind of leading towards, is how might you take just regular 2 wires, and in this case is more of a solenoid, but the twisted wires, and do something better with them. So that's kind of the design behind that one. C is the Faraday's Law. Explain why is there even a back EMF in a coil when the coil is first connected to the battery? Yeah, that's the Faraday's Law, right? That is, there is a back EMF that is directly proportional to the change in flux. And so if you were to take a battery with a switch S and connect it first to an inductor and then to a resistor, what happens when you close that switch? And we calculated this, and I think we're going to need it to solve some of these problems coming up. But we learned that the current, as a function of time, started at 0 and ramped up to a maximum of V over R. But the reason it did not go up to V over R right away was because of this back EMF. This back EMF was Faraday's Law. We said that as you were trying to put the current into the inductor, there would create then a field, and I guess it depends on which way you wind these. Kind of in my picture, I guess I was kind of saying that would be the field. And that's what I would call the primary field. That's the field you get from the current in the wire itself. So therefore, we would want, and nature would induce, a secondary magnetic field, a field that would oppose the change. And so that would make an EMF or a current going in the other direction. And maybe I'll just put EMF in the secondary like that, saying it would oppose that change. And so that's our Faraday's Law. Our Faraday's Law says that we have an EMF or an electric field when there's a change in the magnetic field. And so the intent of this problem is just to say, hey, it's a Faraday's Law. It's one of these fundamental parts of our electromagnetics. That if there's a change in the magnetic field, then there is a EMF that opposes that change. And so that's what's going on in these inductors. And they can be used for different reasons. Of course, when we put them in our AC circuits, we refer to it as Eli. And even though I didn't use the phrase Eli back in that chapter, I might as well phrase it now. Do you get that EMF before you get the current? And so there's this back EMF, then there is the current. Yeah.
So you're saying, if you curl the inductor the other way, the back EMF is actually going with the EMF from the battery?
Yeah. Because so the EMF would be in the wires, because it would be a back. And so I would go this way, and then this way, and then this way, and then this way. Yeah, and I would kind of trick it to act like it doesn't have any inductance. Yeah. Now, granted, if you don't want to have any inductance, why wrap it in a little coil for the first place? I get that. But there are the whole idea of we've got these long transmission lines that we want to send our data to. And if they're just 2 lines, then there's flux between them. And so it's best to twist those wires if you've got to send your data, 3, 4, 5 feet or longer. Yeah.
So the electric field and magnetic field always point in the same direction?
No. I would even say these aren't really the same direction because the electric field, not really shown here, maybe I should have tried to draw it better, is actually curled in the wire itself, right? The electric field is really like that.
Okay, so I mistook the E for being electric field. That's just the EMF, the E.
Yeah, that was kind of the net effect of all the sum of all the curls. Yeah.
So if you wrap the coils in the opposite direction, so the back EMF was in the same direction as the current, would the graph just, like, would you not get a gradual change in current? Would it just go up?
No. Yeah, actually, a good point. If I curled the wire the other way, the result of the graph is still the same. I still get an inductance. The only thing that maybe looked different in my picture, maybe I'll draw both. If I had one coil where the current came, or the wires came over the top first, and I compare that to this one that goes under and then over, in this one, the current would make, and I'll call it the current from the primary, from the battery, would make a field in this direction. Let's see, let's use green. So that would be the magnetic field. Whereas if I had the wires coiled this way, then this would be the field once the current started to go. The back EMF here would want to make flux, and maybe just to do a different color, the back EMF would be this direction. And to get that direction, it would make a back EMF like this, opposing the current trying to go in. And on this one, the opposing flux would be this way, which is coming from an induced current that is going this way, this way, this way, and this way. And it still is opposing the current. So whether the inductor is clockwise or counterclockwise, the effect here is the same. It's when they two are simultaneous in the same one, which was our previous conversation, that they can then self-induce with each other and then cancel each other off. All right, well, here is the second piece of Ampere's law over there, and I'm glad to see I still left it up here, because let me pause here. This says, what are the two fundamental ways of creating a magnetic field? Let me change that question for a second. What if I asked you what were the two fundamental ways of making an electric field? That we've covered. What would you say? Right, charges or changing in magnetic fields. And so this is the one we've learned recently. This is the fact that a back EMF, or an electric field, is created from a changing magnetic field. And many, many weeks ago, way back at the beginning of the semester, we learned the first way to create an electric field. It was from just charges, right? All right. So I would say, and I did say when we started Faraday's Law, that when you guys were on Thanksgiving break, so maybe somebody asked you why you were having Thanksgiving, what did you learn this semester? And you said, oh, there are two fundamental ways to make an electric field. One is with charges, but the other, more interesting one, is changing magnetic fields. In fact, I have a test coming up on it. Let me tell you more. All right. But the same is true about magnetic fields. There's two fundamental ways. We've only mentioned one. It's right here in this term. What is the fundamental way of creating a magnetic field? Okay, currents. But there is yet a second one. that I'll use this as an opportunity to introduce to you. What is this saying? Change in electric fields make a magnetic field. And so hopefully at the end of Tuesday, and I'll bring it up now, is that you'll finish this class going, okay, what are the two fundamental ways of making an electric field? What are the two fundamental ways of making a magnetic field? And I'll repeat with the electric. So electric, what are the fundamental ways of making electric? Charges and changing magnetic field. So what are the two fundamental ways of making a magnetic field? Okay, currents or changing electric fields. And so hopefully you see the symmetry here, that a changing magnetic field makes an electric field. What does a changing electric field make? A magnetic field. And that's this term that I'm going to introduce to you on Tuesday, but I'm going to use today as kind of a stepping stone towards that. That's what that one is saying. And I'm hoping that term looks a lot like this term. Doesn't this say change in magnetic field makes electric? And then this new one to you, what does this say? Change in electric field makes magnetic field. And that's what this question is getting at. What are the two fundamental ways of making a magnetic field? So current and changing of the other field, which in this case is electric. So changing electric make magnetic, and changing magnetic make electric. And so hopefully that will make this next chapter pretty easy to learn, because I would say what we're about to learn is exactly what we did with Faraday's law, but the fields are reversed. Instead of a changing magnetic field making an electric, we're going to say a changing electric makes a magnetic. And that's what I see in that equation as I read the math and say, okay, what's going on in those details. And that's what this one is getting at. Oh, and this one is kind of like the Eli question, although this is the ice question. Why is there current in the capacitor before there is voltage? Let me say more than just ice, but yeah, that's the idea. I think the best way to describe it is you can't have voltage until you have charge on the capacitor, and you can't have charge on the capacitor until there is current. That's what current is. So you're going to have current flowing first, then you'll have it full or partially full, and then you'll have your voltage. The example that I think in one of the classes, somebody asked it, and I just said, well, let's fill up the sink. I mean, to fill up the sink, what do you have to do first? Yeah, so you have to have the flow of water first. Then, after a little bit of time, you now have a full sink. And so you have to have a flow of charge first before you can have charge on the capacitor. I'll unplug the drain there, and so it'll drain out there. But I think that's probably the best approach to that one. And so those are kind of those open-end ones, which there's some on this test and the next test, and I kind of like them. I don't know what I'm going to do with you guys here, so maybe there'll be something like that, or maybe they'll just be short ones. But these make good short ones, especially like Lenz's law. What's the direction? What's the fundamental idea? Shall we go on to the next one? How about number 2 here? And number 2 looks like, I'll have to read it, but it looked like it's a Faraday's law, so it's right out of chapter 31. That then says, what is the induced EMF? And so I'll read it here first. It says a rectangular coil that has 60 turns, has these dimensions, 0.1 meters by 0.2 meters, and a total resistance of 10 ohms, rotates with an angular speed of 30 radians per second about a y-axis. All right, so maybe I'll pause right there. So I'm thinking, okay, so here's this rectangle. And here's a y-axis, and so it is now spinning around a y-axis. I suppose if I grabbed a piece of paper for my rectangle, it would be something like this. Okay. So I have a rectangle, it's got 60 turns, got these dimensions, it's rotating around the y-axis in a region where a 1 Tesla magnetic field is directed along the x-axis. All right, so this would be the x-axis. And so if I have it here and it spins, would there be a change in flux through this rectangle? Well, yeah, right? In this direction, there'd be a lot of flux going through it. And when it gets in this position, there'd be no flux. And so it would be increasing to here, and then decreasing, and then going to 0. And then increasing the other way, and then going to its maximum, and then decreasing back to 0 as it spins around there. All right, so again, I'm going to visualize this, but this is just right away, the first thing that goes to my mind is this is a Faraday's law here. There's a flux that changes. Okay, the rotation is initiated so that the plane of the coil is perpendicular to the direction of B at time equals to 0. Now I wonder what's meant exactly, the plane. So I don't think they want the normal vector. The plane is perpendicular. So I think they're saying it starts this way. And so we start with it like this, and we begin to spin. Okay. So the rotation is initiated so that the plane of the coil is perpendicular to the B field. Write the equation for the EMF produced in this rotating coil. All right, well, like I said, here is the Faraday's law. And Faraday's law says that the EMF is equal to the change in flux. And just to emphasize this, that is the change in flux for one loop in the rectangle. They made it very clear that there were 60 of them. And so I'll just think about one loop here in my rectangle and then multiply that by 60 to get the whole thing. Okay, and so there's my first step in it. I'll do the 60, I'll do the derivative, and then I'll do the magnetic flux. And maybe, again, the first thing I'll do is take a dot product. And start asking you the same questions I asked in class here. Is B a constant? Yeah, and I should ask both. Is it a constant in space? Is it a constant in time? And I think they're implying both of those when they said that the magnetic field is 1 Tesla directed along the x-axis. So it's pointing this way, and it always points that way. And I don't think it matters where I am. It's still trying to say it's 1 Tesla. And so over space and over time, the magnetic field doesn't change. So I can pull it out of here, and I can pull it in front there. How about the angle? Is it a constant? And again, maybe we should separate those to two questions. Is it a constant over space, or is it a constant over time? And so maybe it's a good idea to kind of hold up. Here's my plane. If I kind of maybe give it a little angle and stop it right there. At that moment in time, isn't the angle between the normal vector and the field the same everywhere along this sheet? All right. And so when it was in this location, I would say that angle is 0 degrees. When it rotates a little bit here, now it's 90 degrees. But it's 90 everywhere on here. And when it was something in between, maybe here it was 45 degrees. But again, it was 45 everywhere. So it changes with time, but it doesn't change with space. All right, so what that means is I can pull this in front of the integral of the space, but I cannot pull it in front of the derivative of time because it changes with time. And so there is what would happen to this Faraday's law. And of course this is nice because what does this come out to be? Yeah, that's just the area of the rectangle. Good. And does the area of the rectangle change with time? No, the angle is what changes with time, not the area of the rectangle. So this is a 60, this is a magnetic field, this is then the area of it. And so this, I can take the derivative, and if it'll be okay with you, I'll go back to my rotational mechanics, right, our chapter 10, and I can write angle as a function of time as being something like this. I suppose plus the initial angle to be technically true. I guess even going technically true, we would have the angular acceleration, and that would be the full equation that we learned back in chapter 10. But that's kind of a wasted brain power, I guess, because we're not having it angularly accelerate here. But the big one, I guess, I want to start off with is what's the initial angle? Yeah, and I think the way they set this up, it says set it up so that the plane of the coil is perpendicular to the field. That would mean the area vector starts off in the same direction as the field, which is 0 degrees. And so we can put just a 0 degrees there. So no angular acceleration to our coil. It's just spinning at a constant speed. And the way they described it, it started with an angle of 0. And so I have a pretty easy derivative to do. What's the derivative of cosine? And I guess, is it negative sign? So cosine would be, yeah, negative, and I'm going to put it out here, negative sign, and I'm going to just substitute in the omega t. And then I heard somebody say, don't forget the chain rule. So the chain rule gives me the omega. And so if I put in my numbers, I get negative 60 times 1. What's the area of this thing? 0.1 times 0.2 will be 0.02. And then the angular speed, did they tell me that? Yeah, 30 radians per second, okay. So here is the 30 radians per second. Here then is sine, and this would be the 30 radians per second multiplied by t. And so to put all these together, I would have a 60 times a 1 times a 0.02 times a 30, and that is actually a 36 times the sine of 30t. I'm a little bothered by the negative in there, only because we've been talking always about what is the magnitude of the EMF. And we let our right-hand rule do the direction. We haven't done this much, but if you wanted to write it with the Lenz's law, which opposes the change, that would be a more appropriate mathematical way to write it. And it would be foolish of me to ignore the negative sign here and not here. So I guess I'm looking for how you want me to give this answer. Either way, it should be a plus by the time I either take its absolute value or I put in the negative from the original equation, which is the Lenz's law, which I have hence usually just kind of gone right past and said, oh, we'll just do the right-hand rule for a direction, because positive or negative or clockwise or counterclockwise is really kind of our choice. So sometimes we put the negative, sometimes we don't. And we mostly have not. So I think it would be better without the negative in front. Yeah.
So from the beginning of the problem, the BDA cosine theta?
Yeah.
Cosine theta is expressed to be the angle between the magnetic field and the area vector.
Yeah, because that's the dot product.
So wouldn't initially it be 90 degrees?
I know, I don't think so. I got to admit, and I got to read it again. But the way it reads to me, it says the rotation is initiated so that the plane of the coil is perpendicular. The plane is perpendicular, not the area vector. Remember, the area vector is perpendicular to the plane. Yeah, right? So here's the plane perpendicular to the field. The area vector is that way. So the initial angle is 0. Yeah. And I know because they use that word perpendicular, you want to put 90 degrees. But that is, yeah. All right. Well, so try another one? We getting close to break time?
Why did they give us a total resistance?
Oh, wait, maybe I didn't. Did I not finish? They did give us total resistance. Oh, okay. So in this case, resistance wasn't needed. I would have. The next question could have been, what's the current? So if I wanted to know the current would be the EMF divided by the resistance. And so this would be my 36 sine 30t divided by 10, which would be 3.6 sine 30t. And but yeah, we didn't need. They didn't give us the. Sorry, we all left.
No!
All right. By the way, I'll use this as an opportunity to say Thursday of finals week. You guys in the 10:30 class. What time's your final?
8 a.m.
8 a.m. It's not the normal class time. Okay, so make sure you come at 8 a.m. because if you come at 10:30, the door's going to be locked and no one's going to be here. Okay, don't come at the normal class time. That's for the final, not for the test. Yeah. No, so you guys in the 10:30 class, your final is Thursday at 8 a.m. And you guys in the 8 o'clock section, your final is Tuesday at 8 a.m. So that's not a, and that I don't think will confuse anyone because you normally come on Tuesday at 8 a.m. anyway, so that's fine. But it's you guys at the 10:30 class that I want to keep reminding because it's a little early. Okay. All right. Well, we better keep going if we're going to get close to finishing these in time here. Let me try number 3. Let me kind of clear off the board. Oh, I don't have any extra. I'll make some at the break.
Okay.
Okay. So, gonna change ink here. Maybe I'll get some more on the break here. But number 3 says this: you have an 820 turn wire coil with a resistance of 24 ohms. It has a length of 7 centimeters. It has a cross-sectional area of 1 times 10 to the negative 4 centimeters squared. It's connected in series with a 14 ohm resistor and a 25 volt battery. How long does it take for the current to reach half of its value? And like a lot of these problems, I think the first part of this is just kind of asking, what kind of question is this? You know, is this a Physics 121 problem? Mechanics? No, it doesn't sound like that. It wouldn't be appropriate for this test. So I'm sure you know it has something to do with the material we're talking about here. But doesn't this look like self-inductance? Doesn't this look like an LR circuit? And it might take a little while to notice that, but let's talk about it. We have this battery, okay, so here's a battery. I think I remember reading it's 25 volts. And we've got this 820 turn wire. And it's in a coil. Well, isn't that what we said an inductor was? And so that's kind of the little subtlety in this problem, is to realize then that they are talking about in this problem an inductor. And so we've got this coil. The coil with current is this inductor. Remember, we called them coils and solenoids back when we did magnetic fields, but when we put them into the circuits, we started calling them inductors. And so, and when they got really big, I think a couple times we called them chokes. But whether or not we call them solenoids or coils or inductors or chokes, that's just kind of the difference between what we're doing with them. Physically, they're the same. And so this is an 820 turn wire coil of resistance 24 ohms. Now that's important here because in addition to that, there's another resistor of 14. And so if I'm understanding this right, and granted this has to go back to our chapter 27, but there is two kind of resistors in here. And now I forgot the numbers. The wire itself, just because it's a long, thin wire that makes up the coil, is going to have some resistance. And so just by making